everyone. Thanks so much for the invitation, and it's my great pleasure to give this MI-coupling tutorial at this GEM about the inner magnetospheric waves and their impacts on the ionosphere. So I got a kind reminder from the convener and organizer that there are a number of CEDAR folks in the audience, so I will try to make my tutorial accessible to the broad GEM-CEDAR community. And before I start my talk, I'd like to thank my collaborators at Boston University and UCLA for providing the valuable inputs in this tutorial, as well as the Van Allen probes, Demis, Pose, Barrel, and Firebird and other teams for providing really excellent data extensively used in this tutorial. Okay, so this is my outline. At first, I would like to start with a broad introduction to the connection between the inner magnetospheric waves and ionosphere, and to talk about why the GEM-CEDAR community should care about the inner magnetospheric waves. Then, I would like to go through the several types of inner magnetospheric waves, which are particularly important for the ionosphere. For the wave impacts on the ionosphere, I would like to talk about the three parts, including the diffuse and pulsating aura, and ionosphere conductivity, as well as their impacts on the atmospheric chemistry. And last, I'd like to talk about the outstanding open questions and exciting future opportunities, followed by the summary. So as we know, the magnetosphere and ionosphere is a fully coupled system, which is also highly complicated. So they're coupled through the convection electric fields, and they're also coupled through the large-scale currents, such as region 1 and region 2 currents, which are connected through the ionospheric currents. And moreover, particles trapped in the magnetosphere can precipitate into the upper atmosphere and deposit their energy and cause the ionization. So in this tutorial, I'm going to focusing on the MI-coupling aspects regarding the particle precipitation, because it naturally and closely connects the inner magnetospheric waves and the ionosphere. So as we know, the particle trapped in the magnetosphere, they can precipitate into the upper atmosphere, and the altitude they deposit their energy depends on the species and the energy. So the particles which generate the spectacular aurora, they come down all the way to a couple of 100 kilometers, but the more energetic revision, the particles can come down all the way to the 60, 70 kilometers. And the Brownstorm X-rays generated in association with the energetic particle precipitation can come down all the way to the stratosphere. And this schematic shows the ionization from the various processes. So below a couple of 100 kilometers, where the solar EUV and the X-rays become strongly attenuated, as we can see, the energetic particle precipitation play an important role in ionizing the upper atmosphere. And especially those radiation belt and the Aurora electron precipitations are closely relevant to the inner magnetospheric waves. So wave-driven particle precipitation also causes the spectacular aurora. Like this is showing the diffuse aurora in the sky, and we can see there are also some dynamic structures pulsating inside it, which is called the pulsating aurora. So based on the over 10 years of the BMST statistical betterments, the Wen Li showed that the diffuse aurora provide a major source of energy input into the ionosphere, thus play an important role in changing the ionosphere conductivity. So, as I will show more later, the inner magnetosphere waves play a key role in producing energetic particle precipitation, and those precipitations are important in changing the ionosphere conductivity, which are important for affecting the ionosphere electric field. And those ionosphere electric fields, in turn, affect the magnetosphere plasma transport, which ultimately determines the generation of various inner magnetospheric waves. And in addition, the particle precipitation also affects the atmospheric chemistry and causes the depletion of the ozone. So, to better understand particle precipitation, it's very important to understand what causes particle precipitation, especially about those inner magnetospheric waves. So the overarching objectives of this tutorial are to address those main three questions. So what are the typical properties of the inner magnetospheric waves, and what are their roles in particle precipitation? And what is the quantitative impact of those inner magnetospheric waves on the ionosphere? Okay, then let's move on to the second part about the inner magnetosphere waves. And welcome to the zoo of the plasma wave. And this plot shows the overview figure from the Van Allen probes, showing as a function of frequency and time for the waves all the way from like a millihertz range up to the several hundred kilohertz range. So this thin line here is upper hybrid frequency, and from this we can infer the plasma density. So those two regions are inside the plasmasphere, and this is outside of it. And we can clearly see that just inside the plasmasphere, in this case, excitation of the ULF wave and EMIC waves, as well as the plasmaspheric hiss. But in outside the plasma pulse, we can see the intensification of the strong chorus waves below the electron gyro frequency and the ECH wave above the electron cyclotron frequency. And we can also see the magnetospheric waves generated below the lower hybrid resonant frequency, as well as those kind of electrostatic spikes called the time domain structures. So this cartoon shows the global distribution of those various inner magnetospheric waves, which are potentially important for the particle precipitation. So those are shown in the equatorial plane, and sun is on the top. And the yellow region represents the high-density plasmasphere and the plume. And the His waves are typically observed here, and those often show those kind of broadband structural wave emissions. And the EMIC waves, which are potentially important for driving MEV and sub-MEV electron precipitations, are typically observed in the high-density region just inside the plasma pulse or in the plasmaspheric plumes. And they're generated by the injection of energetic recurrent protons. And outside the plasma pulse, we can often observe those kind of rising tone or sometimes falling tone structures, which is called chorus waves. And they're typically observed from pre-midnight to the noon sector. And outside the plasma pulse, we can also see those type of ECH wave, as well as the time domain structures all the way from the dusk sector up to the dawn sector. And in addition, in the inner magnetosphere, the ultra-low frequency waves are also commonly observed. So as you can see, when those energetic particles, they circle around the Earth, they interact with the various inner magnetosphere waves and change their dynamics, and some of them can precipitate into the upper atmosphere. So how the particle precipitate into the upper atmosphere? So in the basically collisionless magnetosphere, in order to be scattered into the lost cone, the particle have to interact with the waves which has a frequency comparable to their either the gyro motion or the bounce motion. And those effective wave-particle interaction occur when they satisfy this resonance condition, which is the double shifted wave frequency is equal to the multiple of the relativistic electron or proton gyro frequency. So if we take an example of the electron and right-hand polarized Wizard mode wave, and when they satisfy this resonance condition, they can be locked in phase over many cycles and have time to exchange their momentum and energy, so that some of them can be pitch and go scattered into the lost cone and hit the atmosphere and ultimately get lost. And this movie shows an example of how those trapped particles can be lost to the upper atmosphere by interacting with the Wizard mode waves. Okay, it's a little bit slow here. So in fact, the precipitation loss is one of the important loss mechanisms in the magnetosphere. So the dominant approach of quantifying particle precipitation has been the quasi-linear theory, where the effects of waves on particles are treated as a diffusion problem. So in this process, the waves are assumed to have a relatively broad band and small amplitudes. But in fact, some waves exhibit a very large amplitude and discrete elements, which pose a challenge, as I will discuss more later. So based on this resonance condition as well as dispersion relationship, we can calculate the local pitch angle scattering rate for any given electrons and protons when they travel along the field line. Okay? But during this process, since the plasma parameters and wave property vary along the field line, the resonance conditions vary as well. So because of that, we typically take the integral over their bounce orbit to calculate the bounce average diffusion coefficients to evaluate the overall pitch angle scattering rate of waves to the particles. So this figure shows an example of the normalized particle flux as a function of pitch angle. So as you can see, as the diffusion coefficient increases, the loss cone, this is the bounce loss cone, the electron flux inside the loss cone become more and more filled. That means more particles can be precipitated into the upper atmosphere. Okay, then I start to talk about the various type of inner magnetosphere waves from high to the low frequency, starting from the ECH waves. So ECH waves are electrostatic electron cyclotron harmonic waves, and they're typically observed in bands between those multiple harmonics of the electron cyclotron frequency. And those waves are typically confined near the equator and outside the plasma pulse. And the statistical distribution of ECH waves shows that they preferentially occur from the pre-midnight sector all the way to the dawn sector and could be up to the L shell 15. And if we look at their dependence on the geomagnetic activity, we can clearly see their amplitude increases with increasing geomagnetic activity. And those waves are known to be generated by the loss cone instability of the ambient hot plasma electron distribution. And this figure shows the pitch angle scattering rates and the momentum diffusion coefficients as a function of total pitch angle and energy driven by the typical ECH wave. So we can clearly see that the pitch angle diffusion rates are much stronger than the momentum diffusion rates, and ECH wave can lead to the rapid pitch angle scattering in the relatively narrow range of pitch angle, but near the loss cone. So they're important for precipitating electrons all the way from like hundreds of eV up to a few keV. So at the relatively larger L shell, you can see their intensity tends to decrease. However, at the larger L shell, the loss cone is extremely small, and due to the stretched magnetic field topology, the relative weak ECH wave is still shown to be effective to cause the efficient plasmaspheric particle precipitation, and is considered to be the dominant driver of the diffuse aurora in the outer magnetosphere, as I will also show later in more detail. And then let's talk about the chorus waves, which is one of my favorite waves. And they have a frequency like between like 0.1 and 0.8 of the electron gyro frequency. But interestingly, they often have those kind of minimum power at the half of the electron cyclotron frequency. So they typically occur in the lower band and upper band. And they also consist of discrete rising tones or sometimes falling tones. And those waves are known to be generated by the anisotropic distribution of the plasmaspheric electrons. And because of that, they're typically observed outside the plasma pulse, all the way from the pre-midnight sector to the moon sector. And this is a representative example of the global distribution of chorus waves from multi-satellites over a few solar cycle measurements. And in this figure, I'm showing the upper band on the top and the lower band on the bottom. And their intensities are categorized by different levels of the geomagnetic activity. And you can see that the chorus wave clearly depends on the geomagnetic activity. And the lower band is strongest during active times at the L shell between like 4 and 9, and from pre-midnight all the way to the noon sector. But compared to the lower band, upper band is relatively weaker and limited to the lower L shells. And chorus waves received a very intense attention in recent years because they're known to play a critical role in accelerating the seed electrons like hundreds of keV range up to the multi-MeV. And on the other hand, they can also cause the efficient pitch angle scattering of like a few to the tens of keV electrons and provide a major contribution to produce the pulsating and the diffuse aurora. Since the chorus is known to provide a dominant contribution to the tens of keV electron precipitation, the electron precipitation measurements by the LEO satellites are used as a proxy to construct a global distribution of chorus. And the advantage of those type of technique is that those multiple LEO satellites are nicely separated in a broad range of MLT, so they can provide an event-specific evolution of the waves on a global scale. And this is one example constructed based on these pose electron measurements and showing their evolution in the L-shell and time domain at various MLT. And those type of event-specific wave evolution is shown to be critical in capturing the dynamic change in the energetic electron dynamics. And the bursty nature of the cores is also closely relevant to the microburst, which is a short burst of precipitation with a duration of 100 millisecond range. And this is an example showing the microburst. And the statistical distribution of microbursts from the SAMPEX show that those microbursts typically occur from midnight sector to the noon, which is roughly consistent with the preferential region of the cores. And recent conjunction analysis shows that when Van Allen probes observe those type of rising tone chorus waves, the Firebird CubeSats in the conjugate low altitude observed the microburst precipitation, which has a similar duration and cadence with the rising tone chorus. So this suggests that those chorus waves provide a dominant role in causing those type of microburst electron precipitation. Then let's look at the plasmaspheric hits, which are also Wither-mode waves, but they're relatively incoherent and broadband waves, and with frequency all the way from 20 Hz up to the few kilohertz. And hits typically observed in the high density region inside the plasmasphere or plume. And if we look at their global distribution, we found they are also dependent on the geomagnetic activity. But different from cores, they prefer to be stronger on the day side than the night side. And this figure shows the pitch angle diffusion coefficients of typical hits at L is 3.5 and 5.5. And we can clearly see that hits typically cause the precipitation of energetic electrons over the energy from like tens of keV up to the few hundred keV. But their scattering rate is usually not as efficient as cores. But inside the plasmasphere, hits still play a very important role in precipitating electrons through the pitch angle scattering, and is known to be important to create the slot region between the inner and outer radiation belt. And this is another very interesting example from the conjunction analysis between the Van Allen probes and the barrel. And Van Allen probes observed those type of modulation of His wave intensity, and the X-rays detected by barrel shows almost a one-to-one correlation with the His intensity, indicating that those energetic electron precipitation is driven by the modulating His. And Wither-mode waves are also often observed in the plasmaspheric plumes. And interestingly, in this region, the Wither-mode waves exhibit those type of rising tones which are similar to the chorus, but also is with a much longer duration. And recent statistical studies about the plume Wither-mode waves show that their intensity are typically stronger than the typical plasmaspheric hits. And this is one example from the conjunction analysis between the Van Allen probes and poles, which shows that plume Wither-mode waves are more effective in filling the loss cone, as you can see here, compared to the typical plasmaspheric hits, and potentially very efficient in causing the electron precipitation. And the time domain structure, TDS, is a packet of the electric field spikes with a typical duration of millisecond range, and their amplitude could be up to the 100 millivolts per second. And those type of time domain structures are known to be associated with this depolarization injection front, and their global distribution show that they preferentially occur from the dusk to the dawn sector. And those type of time domain structures are shown to potentially scatter the energetic electrons towards the loss cone, especially for relatively lower energy, less than the tens of keV. And in the inner magnetosphere, we have full of nonlinear waves, which form another zoo inside the big zoo of the inner magnetosphere waves. And those include like kinetic fin waves and space holes. And I'm not going to go into too much details here, but I just want to mention that their potential effect into the particle precipitation is still under a very active research. look at the EMIC waves, which are the electromagnetic ion cyclotron wave, typically occur below the multiple ions cyclotron frequency. And they have a frequency in the range of PC1, PC2 from like a 0.1 to the several hertz range. And those waves are generated by the injection of the ring current particles and with energy like tens of keV. And statistical distribution of the EMIC waves and the hydrogen and helium band are shown here from the Themis data. So those waves typically occur in several different regions. One is this relatively overlap region between the ring current and the high-density plasmasphere, and also in the J-H plume region, as well as in the outer magnetosphere, including the dawn sector and the day side. And EMIC waves are known to cause both tens of keV proton precipitation and the MeV and sub-MeV electron precipitations. And here is an example of the isolated proton aurora. And in the conjugate region, EMIC waves, especially in this case, rising tone EMIC waves are detected. And this study shows that EMIC waves are responsible for producing those type of isolated proton aurora. And this is another very nice conjunction analysis between the GOES satellite and the Barrow, where the GOES detected the EMIC waves and Barrow detected the precipitation of relativistic electrons. And they suggest that the EMIC waves drive to observe the relativistic electron precipitation. Then let's move on to the lowest frequency wave, which is the PC45 ULF waves. So those waves, PC45 ULF wave, they have a typical frequency in the range of millihertz to the tens of millihertz. And they have both the alphanic and compressional modes. And statistical distribution of ULF wave power show that they're typically stronger on the day side compared to the night side. And their intensity also depends on the geomagnetic activity. And those ULF waves are generated by the various mechanisms, including the Kelvin-Helmholtz instability near the magnetopoles, and also caused by the fluctuation of the solar wind, especially on the day side, as well as the internal excitation from the free energy in the ion plasma sheet. And the ULF waves has been linked to the relativistic electron precipitation. This is an example from Barrow showing the modulation of the relativistic electron precipitation. And in this case, there was no ULF or EMIC waves are observed in the conjugate location. So by using a simulation, the Brito et al. Demonstrate that the compressional magnetic oscillation may directly generate the precipitation by lowering the mirror points. And other studies also show that the ULF wave can cause the modulation of the aurora electron precipitation through modulating the high frequency wave. So this is one example showing the modulating chorus waves by the ULF waves, and ultimately leading to the modulating pulsating aurora electron precipitation. Okay, and then let me move on to the next part about impact of the inner magnetosphere waves on the ionosphere. And in this part, I'd like to mainly focus on three different aspects, including the generation of the diffuse and pulsating aurora, because it provides a major source of energy input into the ionosphere. And secondly, I'd like to talk about the changes in the ionospheric conductivity, because this is a critical element for the MI convection. And then I also would like to talk about the impacts of the inner magnetosphere waves on the atmospheric chemistry, because it can potentially reduce the ozone concentration, which is important for the Earth's climate. So the ground-based all-sky imager provides an excellent opportunity to monitor the large-scale evolution of the aurora. And this is one example from the Themis all-sky imagers. And diffuse aurora is typically observed in the equatorward part of the aurora oval, and they can be observed in the pretty extensive region. And inside of this diffuse aurora, we can often see these dynamic structures pulsating, which is called the pulsating aurora. So this figure shows the statistical distribution of the diffuse aurora electron precipitation inferred from the X-rays, and the ECH wave, and the chorus waves. categorized by different levels of geomagnetic activity. And we can clearly see that all three different distributions, they have a very similar MLT preference from the pre-midnight to the noon sector. And the quantitative calculation between the various wave-driven pitch angle scattering rates as well as the diffuse aurora observation shows that the Earth's diffuse aurora is generated by the precipitated energetic electrons from the energy of like hundreds of eV up to the tens of keV, and due to the pitch angle scattering. And in the magnetosphere, in the inner magnetosphere, like L less than 8, chorus play a dominant role, but in the relatively outer magnetosphere, ECH waves play a dominant role. And what is the driver of the pulsating aurora? So using the conjugate measurements between the Themis and Themis-Olsztyn emitters, and Nishimura et al. Found almost a one-to-one correlation between the chorus wave intensity, shown in this red line, and the pulsating aurora intensity. And last year, Kasahara et al. Using the electrostatic analyzer in the electron analyzer in the Aracid satellites, which has a pretty high pitch angle resolution to resolve the loss cone, reported excellent correlation between the chorus wave intensity and the loss cone electron fluxes. So those studies, together with other studies, strongly suggest that the chorus wave precipitate the tens of keV electrons into the loss cone through the pitch angle scattering and ultimately drive the pulsating aurora. And pulsating aurora can also cause enhancement in the electron density in the ionosphere, and this is an example from the iSCAT radar. So in association with the pulsating aurora intensification, the iSCAT observed the enhancement electron density all the way down to the 70 kilometers. And this suggests that it is associated with broadband electron precipitation from like a tens of keV up to the couple of hundred keV. And in the conjugate equatorial magnetosphere, they also observed the chorus waves, and they suggest that the observed lower band chorus causes the simultaneous precipitation of electrons and causes the pulsating aurora, which also enhance the ionospheric electron density. Then I'd like to move on to the wave impact on the ionospheric conductivity part. Because conductivity is known to be a critical element because they can affect the ionospheric electric field distribution, which in turn influences the magnetospheric plasma transport, wave excitation, and the particle scattering. So and those kind of processes ultimately determine the particle precipitation. And the particle precipitation, especially the diffuse aurora driven by the inner magnetospheric waves, is essential for the conductance calculation. And then the next question is how to specify the aurora conductance. And there are three different methodologies used in the committee, including the empirical formula and transport code and a global IT model. And all of those models need the particle precipitation as a critical input. So the next challenging question is how to specify the particle precipitation. So there are also three different approaches, and the first one is the empirical method. So in this method, community get the particle precipitation either from the statistical distribution of the particle precipitation data or inferred from the aurora morphology, and which is plugged into the empirical formula such as Robinson's equation to calculate the conductance. Since this method is based on the empirical distribution, it may preclude the specification of the small-scale and transient variation in both space and time. And the second methodology is from the MHD parameterization. So in this approach, MHD models extract the precipitation number flux and energy flux from the MHD parameter like a temperature and the electron density, and which is used and input into the empirical formula to calculate the conductance. However, those kind of approach may not capture the particle precipitation driven by the kinetic waves very well. And the third commonly used approach is the kinetic approach. So method, the particle precipitation are calculated either by the lifetime empirical method or by calculating the pitch angle diffusion coefficients from the wave-driven physics, and which is used as input to calculate the conductance. But this type of approach requires the accurate specification of the waves and the plasma on a global scale, which is often very challenging to obtain. So I'm not going to go into too much details in each model, but in 2 years ago at GEM, I gave a very nice tutorial about the conductance challenge. Okay? So in summary, the message I got is that specifically specifying particle precipitation in a self-consistent and efficient manner still remains as an outstanding challenge. Okay, and then let's move on to the third wave impact to the atmospheric chemistry. So as I mentioned before, the particle trapped in the magnetosphere, they can precipitate into the upper atmosphere, and those relativistic electrons, they can precipitate all the way to the thermosphere and mesosphere, and create the hydrogen and nitric oxides, which can further react with the neutral atmosphere to reduce the ozone concentration through a chain of chemical processes. So especially in the polar winter, the NOx created in the mesosphere can further transport it down to the stratosphere and reduce the ozone concentration there. So as we can see, the energetic electron precipitation can indirectly affect the Earth's climate through reducing the ozone concentration. So Truman and al. 2016, they modeled one of the pulsating Aurora event, which I introduced before, and using an ion and neutral chemistry model. And so this shows the enhancement in the electron density caused by the pulsating Aurora, which lead to the enhancement in the NOx and HOX concentration, ultimately leading to the depletion of the ozone by 14% at 75 kilometers. And there are more examples. And the climate model called WEGM, they simulated the NOx concentration during the Halloween 2003 event. And in this simulation, they only considered the stellar protons and Aurora electron precipitation with energy less than 30 keV. But what they found is that the simulated NOx concentration is underestimated compared to the observation. So they suggested a full spectrum of precipitating electrons, especially for the relativistic electron precipitation, is required to better understand the impact of the particle precipitation into the atmospheric chemistry. And here's one more example showing the impacts of the relativistic electron precipitation. So using an ion-neutral chemistry model, Truman and al. They successfully reproduced the enhanced electron density all the way down to the 50 kilometer, and which ultimately lead to the enhancement in the NOx concentration. And interestingly, you can see that this NOx concentration enhanced much longer time compared to the precipitation event itself. Okay, so over the past years, our community made a remarkable progress in understanding the inner magnetosphere waves and their impacts on the magnetosphere and ionosphere. And in this tutorial, I mainly focus on their impact in the ionosphere, and I believe the later InterMag tutorial will cover their impacts on the magnetosphere. However, there still exist outstanding open questions and challenges. So, for example, what are the quantitative role of various inner magnetosphere waves, including those zoo of nonlinear waves in energetic electron precipitation? Do we know the physics well enough to identify the driver of each type of particle precipitation? And most of the large-scale models use the quasi-linear theory to quantify the wave-driven particle precipitation effects. But as I mentioned before, some of the waves, they have very large amplitude with the discrete structure where the quasi-linear theory may not be valid. So how important are the nonlinear effects of the waves on the energetic particle precipitation is another big challenge. And now we're in the era of big data with the growing satellite measurements and the ground-based observations. And how to take the full advantage of the rapidly growing big data together with the state-of-the-art models to specify and predict the global distribution waves remains another outstanding challenge. And in this case, the machine learning and the data assimilation approach could be particularly useful. And the inner magnetosphere populations are coupled with thermosphere and ionosphere, but the physics linking them are very, very different. So how to incorporate those kind of microscale wave dynamics into the macroscale models in a more self-consistent and efficient way to ultimately specify and predict the particle precipitation is another major challenge. So the ongoing and the upcoming focus groups, including like EMIC and a new radiation belt as well as the ULF focus group, will continue to address some of those challenges. And here, I also listed the currently available resources which we can potentially use to study the inner magnetosphere waves and wave-driven particle precipitation. So for example, in the equatorial magnetosphere, we have those banana probes, STEMIS and MMS and LRC, which can detect the magnetosphere waves and particle injection. And in the low altitude, we have a variety of the LEO satellites, which can measure the particle flux, as well as the radars and rheometers, which can infer the particle precipitation. And moreover, we also have a variety of the all-sky imagers, which can monitor the large-scale aurora evolution on a global scale. And in addition, we also have magnetometers or VLF receivers on the ground, which can measure the waves on the ground, which are probably propagated from the equatorial magnetosphere. To a step further, if we know the physics of particle precipitation enough, we may be able to infer what's going on in the equatorial magnetosphere, including the waves and particle dynamics, from the LEO satellite measurements or the ground-based observation to some extent. And the more exciting thing is there are more things to come. So here I listed some of the currently operating or upcoming new SmallSat and balloon missions, including the Firebird H6 and 10 and Elfin and Barrow and other satellites. And there are also new exciting missions coming up over the next several years, including the Rio, Serbi, and GTO-SAT. And I strongly believe that those small SATs, balloons, together with the magnetospheric satellites, will provide an excellent opportunity to further understand the wave-driven particle precipitation in the near future. So to summarize, the inner magnetosphere waves play an important role in precipitating the particles trapped in the magnetosphere into the ionosphere over a broad range, all the way from the 100 eV up to the several MeV. And those wave-driven particle precipitation cause the spectacular aurora, like diffuse and pulsating aurora, and they also change the ionospheric conductivity, important for EMIC coupling, and they affect the atmospheric chemistry to reduce the ozone concentration. Although there are still open questions or challenges in understanding and quantifying the wave-driven particle precipitation, exciting future opportunities are available to address some of those challenges. So at last, I'd like to mention that if someone asks, who cares about the blue of the inner magnetosphere waves? And I hope the GEM-CEDAR community will say, yes, we care. Thank you very much for your attention.
Thank you, Wen Li. I like the talk from the beginning to the end.
Thank you.
Every page was so impactful. And I also thanks Charlie to record everything so I can go back and then hear more and more over and over again. Okay, good. So here's a question. So when waves is really confusing to me all the time. But when I jump in the EMIC coupling field, I cannot avoid studying these, waves. So that's why I recently started to looking into the ionospheric waves and then how to connect that wave-particle interaction and how to calculate the exact precipitation. And then I found really nice papers from you and Magnetosphere and you guys working hard. And when I look at the map, you guys using the AE below 300, above 300 nanotesla. As an ionospheric scientist, that's really, I mean, you can see several thousands of nanotesla. So I was just curious that would you go back to that map of Meredith maybe,
sure,
so people can see?
Yeah, I can do that.
Oh, thank you. Yeah, so I wish we can have a more variety of AE values there. And is it possible, or do we don't have enough data to do that?
Yeah, thanks for your kind words. And yes, so this is a map from 7 years ago. Since then, the community has made great progress. And the reason at that time why we use these 3 different levels is because of the data coverage. If we use like a very extreme condition, like a larger than 1,000, there are not enough data to give us statistically reliable results, and that's why we use this to reflect the dependence on the magnetic activity. But indeed, with this big data era, it's quite possible to categorize them in a more comprehensive way, or either by binning with smaller beams in AE, or using the machine learning techniques to get a more dynamic evolution in the wave data. So nowadays it's definitely possible, and this is one of the representative examples, but 7 years ago. Yes. Yeah.
Thank you very much. I'm glad.
Thank you very much for the excellent talk, and special thanks from CEDAR community for putting highlight on ionospheric effects. I'm very curious about nonlinear waves that you mentioned. I know it's a very complicated topic, but maybe you have some insights. How can we proceed to understand effects of nonlinear wave for Aurora?
Nonlinear wave for Aurora. That's a good question, and to be honest, I'm not an expertise in nonlinear waves. Is there any nonlinear expert in the community? Like Malaspina or Moser, Agapitov? No? Oh, Jacob. Do you want to comment on that?
Sure, okay. I'm not GEM chair for a moment. Nonlinear waves can sometimes do unexpected things qualitatively. In other words, linear waves, you would turn up the amplitude and turn up the response in a linear way. Nonlinear waves have this tendency where you turn up the amplitude and suddenly, instead of expanding your diffusion, particles just go whoop, and they either go off to very high pitch angles or low pitch angles. They get phase trapped and get caught and accelerated very rapidly. So the overall effect of nonlinear waves is still TBD, but the unfortunate part is, instead of just considering a frequency and let's say what else, wave normal angle, you have to include amplitude as well as a parameter in your wave, which makes things a bit more tricky.
That's a very good input. I thought when I heard about nonlinear wave, it's like a nonlinear zoo. But if I'm talking about like a discrete coral sweeps, yes, we did do some analysis about their impact. And Jacob just mentioned the phase trapping and phase bunching, those kind of effects could be potentially important. But with including those kind of amplitude modulation, then the pictures start to become very interesting. It starts to become more quasi-linear type of interaction. But as Jacob mentioned as well, it's still under active investigation now. Yeah.
Take one more question.
Yeah, I'm really heartened by your challenge of the difficulties of trying to specify conductivity in terms of precipitation. It's extremely important. And I'd like to make an appeal that goes beyond Drew's request, which is to look for causal regulators of precipitation. AE, KP, etc. are not causal regulators. And if we want to embed these effects in global simulations, we need to have some way of specifying the precipitation into the loss cone that's going to produce diffuse aurora or whatever, that we can embed in a global simulation, causally regulated, so it's all self-consistent in some way.
That's a very nice comment. I hope with the ongoing and upcoming focus group activities, we will be able to address some of those challenges, especially those conductivity challenge.
Okay, think we'll stop there. Before I let her go, since Wen will never boast of her own achievements, I'll do this on her behalf, and sorry to embarrass her. We're very proud of Wen for being a recent NSF Career Award winner, so congratulations.